we got to do. One more thing. This was yesterday's stuff. We went through the Arrhenius equation and how you could use this particular equation in order to find rate law constant at various temperatures. We talked about finding the activation energy through a graph. Actually, I didn't assign it. Well, I did, but then I removed it. But number 60 in your book is very much like this, where it actually asks you to graph it. I just decided not to have you do it because it's sort of difficult to graph it on a sheet of paper in your notebook. But it's that idea behind it. So you might want to at least give a peek to that question. But what we need to talk about now is a slightly different topic on the same lines of how reactions occur, and that's the idea of a reaction mechanism. So that's our topic of the day, is a reaction mechanism. So what a reaction mechanism is, essentially, is it's a series of simple reactions which are called elementary steps, and I'm going to spell it right even. That represent the progress of the reaction. I cannot spell today at all. Holy cow. I know, like every other day, right? And we're talking about at the molecular level. A series of simple reactions, elementary steps that represent the progress of the reaction at the molecular level. So I want you to envision this reaction here. These are gases, plus fluorine yields 2NO2F, gaseous. And I also want to remind you some of the stuff we talked about yesterday, the fact that we know that reactions depend on several things, such as P, the steric factor, which is related to the orientation of molecules, and Z, the collision frequency, the fact that they've got to be colliding often enough, and F, the fraction that has enough activation energy. So the reason I bring that up is because if we look at this equation right here, in order for this reaction to react, it actually is pretty unlikely it would react at all. And the reason I say that is because what we really have is we have 3 molecules. Now, if you think about what those 3 molecules have to do, they would all have to collide at the same time, all 3 of them. Not only would they all have to collide at the same time, they would all have to hit hard enough that they would be able to react and bonds could break. And they would all have to be oriented in the right way. So they have to hit exactly at the same time, they all have to be oriented correctly, and they all have to be going at the right speed. And then and only then would the reaction actually occur. And when you think about that, it's kind of unlikely that the reaction would occur most of the time. So that's probably not what happens. And that's why we have this idea of a reaction mechanism, that it probably doesn't occur in one step like that, but in fact it probably occurs in several steps. So that's what we're going to be talking about today. Those steps are known as elementary steps. So I need to give you some rules for elementary steps, and I'm going to go through a couple of examples with you. The first rule. The elementary steps must add together to give the balanced equation. Like these are, this step happens, and this step happens, and this step happens, but ultimately when you're all finished, they need to add up to give you the equation you were interested in. That one is pretty simple. second one, the second rule. The rate determining step, which I'm going to mention in a second, should predict the same rate laws as found experimentally, and it can be written directly from its molecularity. I will tell you what that means. So molecularity is a vocabulary term that really is talking about the number of molecules reacting in an elementary step. And then there's some other vocabulary that goes along with it, like we might use the fact that something is unimolecular, which means there's only one molecule reacting in the elementary step. Or maybe it's bimolecular, where there's two molecules. Or maybe it's termolecular, where there are three molecules. But this one, you guys, is very unlikely, for all those same reasons that we just mentioned. Because if you suddenly start having three molecules, now they all have to hit at the same time with the right amount of activation energy and the right orientation. And it's sort of unlikely. But one or two molecules are certainly more likely in that respect. What I want to do is go through two examples so we understand what that actually means. So I want to do two examples with you. First one, I'm going to use that same equation I just gave you. So NO2 gas plus F2, and there were two of those, yielding 2NO2F. Scroll up. And what we're going to look at is, I'm going to tell you the experimentally determined rate law. We got that? We good? So somebody did an experiment and found out that the experimental rate law, much like you guys did with the iodination of acetone, you guys figured out what the rate law was, that the rate law for this is rate is equal to K times the concentration of NO2 times the concentration of fluorine. So it was first order with respect to NO2, first order with respect to fluorine, second order overall. Now what I'm going to give you is I'm going to give you a proposed mechanism. Now, first thing I want to do is make a note to you, you guys. With a proposed mechanism, you will not have to come up with this on your own. I am giving this to you. We are going to evaluate it. You do not have to make up mechanisms. So I don't want you to think, how would I come up with that? You don't have to. You just need to be able to evaluate them, which is what we're going to do. So I'm going to give you a proposed mechanism, a series of steps by which this might have happened. So here's the proposed mechanisms. 2 steps. First, maybe one of the NO2s bumps into one fluorine in order to produce one of the products, NO2F, but it also gives off a free radical fluorine. That's the fluorine that's not F2, which obviously doesn't like to exist. We know fluorine is diatomic, but so it's probably going to react right away. Second step, maybe another NO2 comes along and it bumps into that free radical fluorine and it produces the other NO2F product. So notice that this step is bimolecular because it's got two molecules hitting together, and this other one is also bimolecular. Far easier to have two molecules hitting each other than three. The other piece of information I am providing for you is the fact that whoever came up with this mechanism decided that this was the slow step and this one was the fast step, which will come into play in a little bit. Here's the question we are going to seek to answer. Is this a valid mechanism? And the way we're going to answer that question is really by seeing if they follow the rules for elementary steps. So we want to know, in order to answer that, does it add up? Do the equations add up? And does it agree with the experimentally determined rate law? Always do the add up one first. It's the super easiest one to do. You can almost eyeball it, but if it doesn't add up, you can stop right there. It's not valid. So we're going to go ahead and add these two equations up. And anything that is produced by one and used up by the other we can cross out, like these free radical fluorines, right? They end up getting used up and being produced and used up. So what we are left with then is 2NO2 plus F2 yields 2NO2F, which absolutely matches the one I gave you originally. So check. The answer here is yes, they add up. So we checked that part. The second question is, does it agree with the experimentally determined rate law? So in order for us to answer that, let's go back up to the rules for elementary steps over here. It says the rate determining step should predict the same rate law as is found experimentally and can be written directly from its molecularity. So let me show you what that means. First of all, we need to know what rate determining step means. So the rate determining step essentially is a result of the fact that reactants can become products as fast as they can complete the slowest elementary step. Which means the rate determining step is the slowest elementary step. So when we look at a mechanism, and I told you one reaction was fast and one reaction was slow, the rate of the reaction is not determined by the fast step, even though it's fast. It's actually determined, when we look at this, it's determined by the slow step. So this particular step is the rate determining step because it's the slow step. And so I want you to envision if we were having an AP chemistry field day. You guys remember doing that in elementary school? Field day? You guys did that, right? Some of you didn't? Yeah. So let's say we were having an AP chemistry field day and we decided you guys are going to break up into teams and we were going to do relay races. And let's say that David, Sam, and Greta, you guys made up a team of 3 for your relay race, and you guys made up a team of 3, and so on and so forth. And let's say it was the day before our field day, and Greta here tripped and broke her kneecap.
Not even a twisted
just full on broke her kneecap. I have broken my kneecap. I've had a lot of issues. No, I've had my ACL. Like over the summer, I had my ACL repaired, but like, I think my daughter was 1, so like 13 years ago, broke my kneecap. This is what you did. Yeah, I'm sorry, Greta. It's an unfortunate incident. At any rate, Greta is a trooper, so she is going to run that relay race anyway, cast and all. She has some crutches, too. So we get to the day of the relay race, and everyone runs the relay race, and you guys lose. Sorry. Well, let's say prior to the race, David is cheerleading here. He's going, come on, you guys. Sam, you and I have to run like twice as fast to make up for Greta because she's really pokey on her crutches. She doesn't even know how to use crutches. She just got them yesterday. Okay, so David and Sam, they run their butts off. Do they win? No, they still lose. Why? Because it doesn't matter how fast David and Sam are running. Greta takes longer than like their entire team to do their entire relay before she can finish her leg of it. In chemical reactions, it's no different. You have different legs of a chemical reaction. Those are the different elementary steps. It doesn't actually matter how fast the fast steps are if the slow step is slow. Which also means that if I want to speed up a chemical reaction, that's the one I want to concentrate on, is the slow step. If I want to speed up this relay team here, I can tell Sam to run faster. She might, in fact, run very fast, but that's not going to speed it up. I got to speed up Greta. We stick her in a wheelchair and we push her. Is that going to help that team go faster? Sure. So my goal with a rate determining step is, this is the step that determines everything. The rate is what is going to be determined by how slow that is. If I want to speed up this entire reaction, this is the step I need to focus on, because that's the one that makes the difference. All right. So back to, does it agree with the experimentally determined rate law? Well, that whole sentence about I can write the rate law from the rate determining step, which is this one, means rate equals, okay, I'm writing the rate law directly from the rate determining step. Rate is equal to the concentration of NO2 times the concentration of fluorine. And that part where it says it can be written directly from its molecularity means that the fact that this is one NO2 and one F, that absolutely tells me that the powers are one NO2 and one 4F. Remember when I said you can never, don't ever use the coefficients to write the rate law? Remember when I said that? That's still true. We would never use these coefficients to write the rate law. But in an elementary step, you absolutely will use the coefficients in an elementary step to write the rate law. So this is the rate law that the rate determining step tells me. The question is, does it agree with the experimentally determined rate law? Does it match up what I gave you? Yeah. And the answer is yes. And so since this answer is yes, the original question that we were seeking to answer, is this a valid mechanism, depends on your answer to these two questions. Does it add up? Yes. Does it agree with the experimentally determined rate law? Yes. If those two questions are yes, then this is a valid mechanism. It doesn't mean it's the only mechanism. This is not telling you, oh, well, that absolutely is 100% the way that occurs in real life. That isn't what it means. Someone else might propose another mechanism that might also add up and agree with the experimentally determined rate law, and so that one might also be a valid mechanism. The only way to tell is if we like magic school bust ourselves inside and watched it happen, which is a little difficult, I would say. So this is just saying, is this a possibility? Yep, this is a possibility. Questions on that? I have one more example I want to do with you. Rahul? How did I determine the two were? The way you mean, how did I determine I was going to write this? Well, this rate law right here that I wrote it directly from this step, which I chose that because it's the slow step. The experimentally determined rate law I actually had given you originally. No, that's okay. So I just literally looked, hey, does that match what I was given originally? Peter. I told you. Yeah, I would have to give you that information or give you the rate law, and maybe you'd have to pick which one was slow and look which one matched the rate law, that kind of thing. But yeah, I'm not expecting you to come up with that information on your own. Again, I'm not expecting you to come up with the mechanism itself either. Okay? All right, let's do one more example. All right, let's say we had ozone, O3, that's ozone, by the way, turning into oxygen gas. And the experimentally determined rate law is rate is equal to the rate law constant times the concentration of ozone to the second power over the concentration of oxygen. So this rate law is second order with respect to ozone and -1 order with respect to oxygen, which is a little weird, of course, because oxygen is not a reactant. So how do we know that it's this? Because I'm telling you. Apparently, when they did this experiment, they found that they couldn't really get the rate with respect just to ozone. You know, sort of like when we did the iodination of acetone and we had that hydrogen ion concentration which was in there, which was not a reactant. So it's weird, but this is what it is. So I'm going to give you a proposed mechanism for this, and we're going to try to figure out if it's valid. So, is the following mechanism valid? And here it is. First step. An ozone molecule breaks up into oxygen and a free radical oxygen, and it turns out that this one actually ends up being at equilibrium. Second one. Free radical oxygen bumps into another ozone molecule and forms two oxygens. First step is predicted to be the fast step. Second step is predicted to be the slow step. This first step, you guys, here's an example of unimolecular, starting with just one molecule, as compared to the second step, which is bimolecular. All right, so two questions to figure out if it's valid. First, do they add up? Do they? Yeah, so free radical oxygens will cancel. And so we end up with 2O3 yields 3O2. We're good. Always check that first. It's simple to check. All right, so that's valid. Which step is my rate determining step, first or second? Second, absolutely. So our rate law can be written directly from that step. So according to my rate determining step, the rate law is rate is equal to K times the concentration of free radical oxygen raised to what power? What power? 1, because there's only one here and one here, right? Times the concentration of ozone, O3, also raised to the first power. Does everyone see where we got that from? And so if I look back at that original rate law, we go, ooh, that doesn't look like it matches. Except that we have a problem in this one. Here's the problem. You cannot leave intermediates in the rate law. What do I mean by an intermediate? Who's an intermediate? Margot? Yeah, it's in O because it is O, and it's because it's in both of the reactions, and specifically because it's being produced by one reaction and used up by the other reaction. So it actually isn't ever present in any appreciable amounts. It's being used up, produced, used up, produced, used up, produced, used up. We can't measure that. And if we want to measure a rate, we need to have something in here we can measure. So we need to get rid of that free radical O, which is not measurable. Question? No? Okay. So here's how we're going to do that. We notice here that this particular step is at equilibrium. And I know that the definition of equilibrium means that the rate of the forward reaction and the rate of the reverse reaction is equal. That's the definition of equilibrium. Those two rates have to be equal. So I am going to write the rate law for the forward reaction, and I'm going to write the rate law of the reverse reaction. I'm going to put them equal to each other, except that suddenly I'm writing multiple rate law constants, so I want to distinguish between them. So I'm going to go back up here, and I'm going to call this K for the forward reaction. I'm going to call it K1, because I'm going to write a rate law for the forward reaction. And then I'm also going to write a rate law for the reverse reaction, so I'm going to call this one K minus 1. But then I also have to write, in fact, I already wrote a rate law for the slow step, and I'm going to call that K2. There's absolutely no meaning behind those labels. So if I go back to my rate law, I'm going to call that K2, because that's the K I'm using for the slow step. So my rate for the forward reaction, the rate law for that forward reaction is going to be K1 times the concentration of ozone. That's my rate law for the forward reaction. Rate equals K1 times the concentration of ozone. For the reverse reaction, it's going to be K minus 1. So now I'm looking as though it were going in this direction. It's going to be K minus 1 times the concentration of O2 times the concentration of free radical oxygen. That's what its rate law would be. And because those two rates are equal, I can set those equal to each other. Now my job is, I'm going to go ahead and solve this for oxygen and then get it plugged in to my rate law. So let's go ahead and solve this for free radical oxygen. So that is equal to, just doing a little algebra here, K1 times O3 over K minus 1 times O2. We'll pause during announcements. I don't know, no explanation for that. All right, anyway, back to this thing. So we had solved this for free radical oxygen, and so now we're just going to literally plug it into this original equation here and solve for that. So if I do that, so I get, of course I did that so it comes off my screen. So rate equals K2 times, now I'm subbing this in, K1 over K minus 1 times O3 over O2, and then I have that original O3 that was in there. And this was K2 originally. If you take a constant times a constant and you divide it by a constant, what do you get? It's a constant. So I'm just going to call that new constant K. I could call it K3. I don't know. We'll just call it K because we're really, yeah. And then O3 times itself, that's O3 squared divided by O2. And now this is what is left when I got rid of free radical oxygen out of the rate law. And so the question is, does this agree with the experimentally determined rate law? Back here, up here. Does it agree with that? Yes. And so it agrees. And so that means that this is a valid mechanism. Phew. That was good stuff right there. All right, so what that means now is you have to practice some of this stuff. These first four blues that you have, 64, 68, 72, they're going to deal a little bit more with the Arrhenius equation, things like that. And then 80 deals with mechanisms, and then tomorrow you'll practice more with mechanisms. So you guys have the time right